Let's share. Mhm. Okay. So our topic for today is Huffman coding. And in here you have two types of coding method. First is the fixed site and another is the variable size. Let's understand what is Huffman coding, what is coding in general. Coding, not the way in which you write scripts, in the way messages are sent. You have all heard about, I hope you know what ASCII is, right? ASCII stands for American Standard Code for Information Interchange, right? Now, stands for American Standard Code for Information Interchange. Let's start one by one. First is American. So American symbolizes that it's going to be English, right? Okay. Next we have something called a standard code. So standard code, what is that? See, a standard is something that everyone agrees upon. For example, if I want to talk to you guys right now, I'm communicating, interchanging the information, but I'm using a specific code, and the code is the language, right? I'm using English so that every one of you can understand me. Okay, so that's a standard. If I start speaking in my native tongue, then maybe some people might get it and some might won't be able to understand what I'm saying. So when computers are interacting, they also need a standard, and that standard code is defined by ASCII. So some kind of standard code is given, and that is like, for example, capital A is given the standard code of 65. Capital small a is given the code of 97. Similarly, if you talk about zero, the zero symbol is represented by the code 48. So when computer encounters 48, it resembles, it prints out the symbol for zero. If it finds 49, this code will print out one. This symbol. This is the symbol. Okay. Similarly, if the computer encounters 65, then it will print out this particular symbol. And if it encounters 97, then it will print out small a. Okay. And this thing, this thing is called the standard code. And you can see these codes map to certain values. Not values, but some certain symbols. Symbols that humans are able to understand. Okay. And finally, we have information. What is information? These, if I write my name is Ram, then this is an information. And if I'm sending this information to another computer, from my computer to another computer, that's interchange. So when you interchange information, computers interchange information, they don't send in strings. They don't send this characters. They send, because computers only understand one thing, and that's binary. Not even binary, they only understand what? Electrical pulses, right? If the pulse is down, that's zero. If the pulse is up, then it's one. Zero and one. That's it. And to represent this American standard code, this ASCII requires 8 bit. meaning that 8-bit is sufficient for representing all the characters in the American table. Now, why 8-bit? What is bit and what's the relation between them? I'm just going to give you a little bit of uh, information here. For example, if you have only a 1 bit available, then you can fill it with either 0 or 1. So you have total 2 possibilities. Either there could be 0 or there could be 1. Now imagine you have increased it. Now there are 2 bits available. So this one could be filled with either 0 or 1. Similarly, this can also be filled with either 0 or 1. So you have some pattern. You can have, you can fix this and have this pattern, and then you can fix this and have this pattern. So now you can identify 4 unique things. So if I was able to here identify only A, and with this I was able to understand B, and now I can do A, B, C, and D. So I have identified 4 alphabets of the English language. If I have 3 bits, now I can have 0, 1 here, 0, 1 here, or 0, 1 here. And based on that, I will have something like 0, 0, 0, 1, 1, 0, 1, 1. First of all, set all of these as 0. Then again 0, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 1. Now these are again unique. So you have from A to some. You can now categorize, identify 8 characters, 8 alphabets. Now, if I just increase it by 1 more bit, now if there are 4 bits, you can already guess now that I can identify 16 characters, right? Here, I was able to identify 2 characters. When I increase that by another bit, I was able to identify 4. Now I can identify here 8. So the pattern is showing that it's going in 2's exponent, right? So first is for 2 to the power 1, then it was 2 to the power 2, then it became 2 to the power 3, then it becomes 2 to the power 4, and so on. And if you look at this is 1 bit, 2 2 bits, 3 3 bits. So if you have 8 bits, how many characters you will be able to identify? 256. Okay, which is from 0 to 255. And that's why you only need 8 bits to represent the American Standard Code. Now, when information is interchanged between computers, what they do, suppose you have information, say A, B, A, B, C, D. Okay, you're sending this information to the to another to a computer. Excuse me, give me a minute. Next, sorry about that. Um, yeah, next we have suppose, yeah. So I want to send this message A B C D, some type of message. Now to send this message, the computer will first convert it into binary. So A in binary is 65, B is 66, again A 65, 65, then B 66, then C is 67, and D is 68. Okay, first 65 is converted. So 65 is what? 64 plus 1, right? So enable the 64 wala bit. So 1, 32 bit remains 0, 16 bit remains 0, 8 bits remain 0, 4 bit 0, 2 bit 0, 1 enabled, and it is represented in 4-bit formation, so you have to add another 0 at here. 66 can be represented with 64 plus 2, so this bit will be enabled and 64 bit will be enabled, everything else will be disabled. So you have 0, 1, 1, 2, 3, 4, 1, 0. So this is your 64. Next 65 again, you will repeat this one. 0, 1, 0, 0, 0, 0, 0, 1. Again 65. You have 0, 1, 8, 2, 3. And we have 66. 0, 1, 0, 0, 0, 0, 1, 0. 67 will be 64 plus 4. Sorry, 64 plus 3. So I have 0, 1, 2, 3, 4, 1, 1. And finally 68 is just 64 plus 4, 2, 3, 4. This. So you will be sending this message. So how many bytes or how many bits are you sending? How many characters do you have? 1, 2, 3, 4, 5, 6, 7. Total we have 7. 7 times 8. That's 56. Right? So you are sending 56 bits of information over the network. But if you look into this, what are the characters that I'm sending? I have A. I'm sending symbols. Huh? Symbol. And let me write their frequency as well. Symbols I'm sending are A, B, C, and D. Correct? A is appearing 1, 2, 3, 3 times. B is appearing 2 times. C is appearing 1 times, and D is also appearing 1 times. So this is basically 3 into 8, 2 into 8, 1 into 8, and 1 into 8. And if you add them all, you will get 56. Right? So yeah, that's what I'm sending. But here's the catch. What are the codes? The ASCII code. Let me write down the ASCII code first. A is represented with 0, 1, 1, 0, 1. B is represented with 0, 1, 0, 0, 0, 0, 1, 0. Then you have 0, 1, 0, 0, 0, 4 zeros and 1, 1. We have 0, 0, 0, 0, 1, 0, 0. Right. This is what we are sending actually eventually over the network. Now my question is, if only 4 characters are being sent, if only 4 symbols are traveling, then why should I use this much space? If I only need to uniquely identify 4 symbols, then why not just send them by 2? Because 2 to the power 2 will give me 4. So I can identify 4 characters uniquely. But I can only send with 2, right? Why should I use 8 bits when I can do the same with lesser bits? Right? So what I can do here is, let me change this coding. I'm going to code it myself. This is my coding. What is this? Let's say A is represented with 0, 0. B is represented with 0, 1. C is represented with 1, 0. And D is represented with 1, 1. Now if you compare it, A is, there are 3 A's, there are 2 B's, there are 1 C and 1 D. And all of these occupy 2 bits, right? So this occupies 2 bits, this also occupies 2 bits, this also occupies 2 bits, this also 2 bits. So how much is this now? You have 3 2s are 6, 4, 2, and this is 2. So total is what? 10, 14. So I compressed it from 56 bits to 14 bits, right? But the thing, it's not over just now, because even though we have converted it, we have made our own coding, we have to tell the computer, tell the other computer that is receiving this data, that we have mapped these values like this. Instead of A mapping to this ASCII code, we have mapped A to this value. Similarly, B is mapped to this value, C is mapped to this value, and D is mapped to this value. So we have to send that table as well. We have to send that data as well to the receiving computer, right? We have sent the data, that's which is taking 14 bits. But now, once the computer has received that data, this 14 bits of information, it needs to be able to map these back to the original message. And that is only possible if we tell it, this is my mapping. Suppose I create my own language and I'm talking in it, then you won't be able to understand it. For you to understand that, I need to give you that mapping, right? If you guys, I don't know how many, if you have watched Office, it's a British Office, the American sitcom. This there was one character who would talk in a way that with like few words do trick. Why use long words? Why use long sentences when you can fit them in just bits of information, right? So that's what this is also doing. But to understand, but to get the reference, you need to have that mapping, right? You need that grammatic, you need that book, you need that translator. Okay, so we need to send the mapping that A points to 00, B points to 01, C points to 10, and D points to 11. Or alternatively, you can understand this, that I am telling the computer that if you encounter 00, convert it into A. If you encounter 01, convert it into B. If you encounter 10, convert it into C. And if you encounter 11, and convert it into D. I need to send this mapping as well. To send this, what does that mean? I'm telling it to convert into A. A is what? The ASCII code. You have to change it back to the ASCII code 0100000001. B is 01000010. C is 01123411. D is 010000, sorry, 100. So basically I'm sending this matrix. I'm sending this value and this value, that this corresponds to this corresponds to this, and so on. Now, if I want to send this data, I need to calculate it also, this thing as well. So how much is this taking? Sorry. Yeah. How much is this taking? 2 bits, 4 times. So that's 8. 8 bits. And here we have ASCII code is obviously 8 bits. So 8 times 4. That will give you 24. Sorry. 32. Right. So you have 32 bits here as well. Now if you combine these, we get total of 40 bits. And combine it with this one, we are sending actually 40 bits of table and 14 bits of data. So total it becomes 54 bits. Originally we were sending 56 bits. Now we were able to downgrade it to 54, 2 bits lesser. Now you might ask, it's only 2 bits shorter. What's the difference it's going to make? Now look at the data. Data was very small. I had taken only 7 characters. Imagine this expanding into large character sets, right? If there's a huge amount of data, whenever we are sending information, we are always sending it in huge payloads. It's never just 2 to 3 characters or 5 to 6 characters. No, it's going to be hundreds of characters of data, hundreds of thousands of characters of data. Even when you are downloading something, even this information that I'm telling you, the network that it's taking to deliver my voice, it's converting it to information, and that information is getting compressed, and it's then transported over the network. It's transmitted over the network to reach you guys. And if this data was not compressed, then what would happen? It would take a long time. There would be a latency. You would not be able to what do you say, get the information in real time, right? There would always be a delay. And if a package is lost, if we are using TCP connections, then what would happen? We will have to send this data again. If you think about when you are downloading something, when you are downloading an app, that app, say it's 1 GB. If it's 1 GB of data that is being sent to you, after you have downloaded the app, once you open it, it re it decompresses. Does that make any sense? Imagine you are downloading WhatsApp. Okay, you have downloaded WhatsApp. WhatsApp takes what, 40 50 MBs, 50 60 MBs. After you have downloaded it, then you install it, and by the time you have finally logged into your account, it's already 200 MBs. It's taking up 200 MBs. And obviously after some usage, after some memory being some cache vache, it will become 1 to 2 GB, 2 to 3 GB. That's because of the media. But remove the media part. You have just logged in, you have created your account, and it's already will be in the hundreds MB range. Or if you have installed a game, right? If you have installed any game, if any of you have played BGMI, PUBG, or any type of game, then that also, if it's say 1 GB of data, after you have downloaded that, you need to re-download the packages, right? It decompresses. Or if you have downloaded zip files over the internet, if you download zip files are what, compressed files. If you're sending someone say a movie, and the movie is say 2 GB of space, taking 2 GB of space, then you will just compress it, convert it into say 1 GB or 1.5 GB, and then you will send that, right? If you have some shortage of internet bandwidth, then that's what you are going to do, correct? And this type of compression is called the Huffman coding. We get these type of compression. There's obviously more uh, complex algorithms there out there, but this is one of the easiest one, Huffman coding. Okay, let's take another example. Wait a minute. Okay. Do you have any doubts still here? were you able to understand how this table was created? If you were able to create this table, if you understood how this table was created, how we created the code part, then only you are, and you also understood why the data part is 14 bits long, this part, and why we have to send 40 bits. If you have understood that much, I will move forward to the variable length coding. This is fixed length coding. All clear?
All clear, sir.
All right. At any point, if you have any doubts regarding any topic that I'm teaching, just stop me in the middle. Okay. All right. Let's move to the next piece of information. Okay. Now let's take another example. Say we have a message B A B B C A D B A C E B C C A E, and let's take a few more. Why not? A B. All right. A B C D E. All right. All right. Let's move forward. Let's create a table first, because obviously we are not going to send this data, right? How much is this data? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20. 20. So 20 into 8, that's 160 bits of data. So if you send this, it's going to take 160 bits. Okay. So obviously we are going to do some compression here. Let's create the table. First of all, symbol. Next is the uh, what was I mapping
Frequency.
it to? Frequency, right?
Frequency.
Right. Yeah, frequency. Then we have the code. I'm not writing the ASCII code. I hope you understand that it's going to be 8 bits long and it's going to take 160 bits. This code is our own code. Symbols we have A, B, C, D, and E. Right? We have 5 unique symbols. Let's write down their frequency. 1, 2, 3, 4, 5, 6. Okay. This happened 6 times. B occurs 1, 2, 3, 4, 5, 6. Okay. This also occurs 6 times. C occurs 1, 2, 3, 4, 3, 4. Okay. 4 times. D occurs 1. Yeah, 1 times. E occurs 1, 2, 3. Okay, 3 times. Now we need to convert it into code, but we cannot use 2 bits. Why? Because with 2 bits we can only identify 4 characters, but we have 5 characters here, right? So we have failed that one. If we do here fixed length coding, okay, let's let me just show you one fixed length coding as well in this example, and then we'll move to the variable length here. Fixed length code. Okay, fixed length code. We cannot do 2 to the power 2 because 2 bits are not going to be sufficient to handle 4 unique characters. So we are going to go to the next big thing, which is 2 to the power 3, that is 3 bits to represent it, because 3 bits can contain data from 0 to 7. So they can identify 8 characters uniquely. So I'm going to assign them one by one. Let's say 000, 001, 010, 011, 100. Okay, done. Now let's calculate what is the total data size now. Hmm. This is going to be 6 into 3, then 6 into 3 again, then we have 4 into 3, then we have 1 into 3, and finally we have 3 into 3, right? So this is going to be, this is your 18, 18. So that's already makes it what, 36. Then we have 4, 3, 12. So that's going to make it 48. Then we have 3 and 3 is 9. So that's 12. Add them together and you get 60. So that's about 60 bits. So when you're sending the data, it's going to take 60 bits. Oh, for God's. All right. Yeah. So it's going to take 60 bits of information to send the data part. So instead of say you, this whole thing becomes 60 bits of information. Next, we need to also send the table. What is the table? The mapping. So A maps to this, B maps to this, C maps to this, and so on. Let's see. We have 5 symbols. So that's 8 into 5, because each symbol is going to take 8 bits ASCII code. So that's there. And here we will have what? 5 into 3. 5 into 3, that's 15. 8 into 5 is 40. So 40 plus 15, the table is going to take how much? 55 bits of information. And the whole data is going to be 60 plus 55, that is 115 bits of information. Now, do you see the reduction? You were sending 160 and now I'm sending only 115. And I have only included 20 bits of data. Sorry, 20 characters here. In the data, there's only 20 characters. But already we have reduced it so much. And this was due to fixed length coding. There's something called a variable length coding as well. Okay, we will start it in a bit. Just go over it. If this makes sense, I'm going to give you another example. Okay, I'm going to give you another uh, message and you have to convert it into this. Okay, you can do it in your copies or you can do it in your notepad, right? Like symbol, use the pipe symbol, frequency, code. Okay, do
Uh,
something.
so this
Yeah.
is the Huffman coding, sir.
Yes. This is
Okay.
Huffman coding, fixed length coding. There's
Okay.
another one, it's the variable length coding. Okay.
Yeah, sure, sir.
Like for this one, I can just convert it into 0. I can call this 0, 1. I can call this 1, 0. This 1, 1. And this one will take 1, 1, 0. Why should these have, why I'm sending 4 extra bits, right? Why should I do that? So
Yeah.
that type of thing. We will understand it in the next one. I'm going to give you a question to try first of all. Okay. If you have, do you guys have any doubt till here? If it's all right, I'm going to give you a question. So you have a message. You have to send this message. The message is say A B B A C D E B C D E A A F F A B B and let's say C C C D E. Yeah, let's take this as an example. Try to do this one. I'm going to turn off my computer screen and I will do it side by side. Then we will compare our answers. Okay.
Yeah, sure, sure.
Compressed size 144 bits. Yup, correct. And what is the total reduction? Yes, yeah, 64 bits. Correct. 64 bits. Wait a minute. 208. Yeah, okay, okay. Yep. 624 bits. How did you get that answer? Okay, okay. How did you increase the size of bits? Okay, Aman, I'm more. Oh, 64 much. Okay, all right. So this is the table that I have drawn. So we have symbols A, B, C, D, E, F. Then their frequencies are like 5, 6, 5, 4, 4, 2. And I have given them these codes 000, 001, 010, 011, 100, 101. Finally, the data came, the original world was 26 into 8, so 208. And in this, the data came out to be 26 into 3 because we have changed into 3 instead of 8. So that's 78 bits. And the table was 48 plus 18, 48 for the symbols and 18 for the code. So that came out to be 66 bits. And the total came out to be 144 bits. So the reduction was 64 bits from 208 minus 144. So that's 64 bit. So that's almost 4 bytes, right? That's 4 bytes of information gone, compressed. And that's how things add up. Now let's talk about variable size encoding. Okay, this was fixed length encoding. In fixed length, we have assigned each of these a fixed length, that is 3 bits. In variable size, what we do is, first of all, to create one, we have to create a tree structure. First of all, we have to write these in ascending order. Mm-mm-mm. So we have 2, then we have 4, 4, 5, 5, 6. 2 is F, 4 is E, D, C, A, and B. That's it, right? Let's draw them. Yes, yes, yes. Okay. First of all, first we need to create these and give that. Yeah. First we have 2. 2 belongs to F. Okay. Next we have 4, which belongs to E. Then we have another 4, which belongs to D. Then we have 5, which belongs to C. Then we have 5, which belongs to A. And finally we have B, which is 6. Okay. Now, do you guys know what optimal merge is? Optimal merge means that you have to always select the merge the smallest values first. In merge sort, when you are merging arrays, merge sort uses two-way merge, right? In two-way merge, you give it, you provide it two sorted arrays, and then it merges them. But there's also merge pattern. If you have say two arrays, then you can follow the two-way merge. But if I have three arrays, then who am I going to merge first? Right? First, I might merge these two, and then I might merge it with this one, the resultant one. So that's just optimal merge. Optimal merge is basically you have to select the fewest element first. So if this element, this array is smaller then this is a little bit bigger, and this is the biggest one. So you will first merge these two, and then you will merge it with the bigger array. So that's basically the thing. Now if you look into this, you have 2 and then have 4. So first of all, these two will merge, and this will create 4 plus 2, 6. Okay. Now out of 6, 4, 5, 5, 6, you have to select two small ones. What are the small ones? 4 and 5, obviously. So I'm going to take this one and this one to create 9. Afterwards, next 6, 5, 9, 5, 6. What are the smallest one? 6 and 5. So I'm going to select these two and merge. And this will become 6 plus 5, 11. Now again choose the minimum. From here I have these two. This is going to give you, uh, let's go. 9, this is going to give me 15. And then finally 15 plus 11 will give me 26, right? And if you look at this count, the top one is the count of the alphabets. There were 26 alphabets, right? See, 26 alphabets were there. That's why the original one was so big. Anyway, now it's done. It's expanded. Now I have to create the coding according to this table. And before adding the values, before adding, making the code, we have to number it. We have to provide zeros and ones somewhere. So if anything on the left of the node is given the value of 0, and anything on the right is given the value of 1, so the branches are marked like left branches are marked with 0, right branches are marked with 1. Okay, so you have here 0, 0, 0. This is right, so 1. This is left, so 0. This is right, so 1. This is right, so 1. This is right, so 1. Left 0, right 1. Now that is done, we can create the table. So we have, um, first of all, symbol, symbol. Then we have its frequency, and then we have the code. Let's write down everyone first. We have, what do you say? A, B, C, D, E. In the table, you don't have to write it in ascending order. It's just to create this tree. To create this tree, we need to put them in ascending order, like here we did, right? That's it. Next, frequency is A appears 5 times, B appears 6 times, C appears 5, D appears 4 times, E appears 4 times, and F, there was also F appears 2 times. Now we have to fill in the code. How to fill the code? Start from the start node. Okay, from the starting, go to A. To go to A, we have to follow this path, right? What are the codes? 1 and 0. That's it. So the code is 1, 0. B. To go to B from the root node, we have to follow this path. So 1 and 1. So it becomes 1, 1. C. C is there. So go this way, this way, this way. So we get 0, 1, 1. Right? 0, 1, 1. D. Everything else is going to be 3 bits anyway. 0, 1, 0. Right? 0, 1, 0. So we get 0, 1, 0. E, 0, 0, 1. Right? To get here. So we have 0, 0, 1. Finally, F. 0 0 0 0 0 0. Now let's calculate the, this is going to be 5 into 2, so that's 10. This is going to be 6 into 2, so that's 12, 12 bits. This is going to be 5 into 3, 15. Then you have 4 into 3, so that's 12. Then 4 into 3, so that's again, what do you have? 12, yeah. And finally, 2 into 3, so that's 6. I think it's kind of similar. Yeah, we are getting kind of similar vibes. Just a few bits difference will be there. Anyway, let's total it out. This whole thing is going to
67.
be, it's coming out to be 67. Okay.
Yeah.
So 67 bits of data, and the table, this is going to be again 8 into 6. So that's what, 48 bits. And this is going to be now 4, 3, 12, 13, 14, 15, 16. 16 bits, right? So this is going to be, your table is going to be 48 plus 16. So that's about 58, 58, 50, 64. 64 bits, right? This is combined becomes 64 bit. So table is of 64 bit, and the total comes out to be 4 plus 7, that's 11, and that's 13. 131 bit. Okay. So we were able to reduce it further, right? With fixed length coding, we got 144, and with variable length coding, we got 131. So we were able to reduce it much more. And you can see that if there's a huge chunk of data, it's going to be reduced further, right? Now, if you think about the codes that you write, assembly code, machine code, C code, whatever you're writing, if you compress that, your C code is
Sir,
made of,
sir, I
yeah,
have a doubt, sir.
yeah.
So is it not necessary to put the smaller value to the left side of the node, or the bigger one is of the right side of the node, sir?
You're
Is
saying
it
that
compulsory or
6,
not?
no, no, no.
जैसे सर
I just,
सर
yeah.
आपने जैसे यहाँ वो 26 किया है ना सर, तो 26 में 11 जो है वो 26 के लेफ्ट साइड होता है और 15 26 के राइट साइड
15, हाँ,
26 सर
नहीं, नहीं. Yeah, you're saying that if you had written it like this, na, you have
11
arranged
को सर हम लेफ्ट साइड 26 के रखें और 15 को राइट साइड सर
15 को right hand side कैसे रखोगे? To do that, you will have to rearrange it, na, in descending order.
Sir, when
Nine.
we extract,
As
sir, main funda of the Huffman coding is we will extract two nodes of the smaller value. So here
Mhm.
one is sir 11 and another one is 15, sir. When we extracted these two nodes and make a new node, sir, new node will be 26. So can we
Yeah,
put 11 on the left side of the 26 or 15 to the right side of the 26?
yeah. No, you can only put them. You're saying that 15 here and 11 there,
Yes, sir.
but in doing so, you will have to shift these values also, na. These values should be there this side.
Yes, sir. Yes, sir. All these values, sir.
Yeah, you can do that if you want to do it. Look, I have made the tree in ascending order of their arrangement. If you just arrange until like 6, 5, 5, 4, 4, 2,
नो नो
then
नो सर, मैं सिर्फ ये कह रहा हूँ सर कि जैसे आपने ये 6 बनाया था ना सर, तो 6 में से 2 को आपने लेफ्ट साइड रखा 6 के और 4 को राइट साइड रखा। फिर वैसे ही जब आपने 9 बनाया सर, तो 9 में 4 को आपने लेफ्ट साइड रखा और 5 को यानी स्मॉलर वैल्यू को लेफ्ट साइड रखा और बिगर वैल्यू को आपने राइट साइड
no,
रखा। जब
no,
आपने
no.
11 बनाया सर, तो 5 को आपने
हाँ,
लेफ्ट साइड रखा और 6 को आपने राइट साइड रखा। तो इन द
हाँ,
सेम मैनर व्हेन जब हम सम करके 26 ला रहे हैं, तो
हाँ
11 जो है 11 वाला जो है वो लेफ्ट साइड होना चाहिए था और 15 राइट साइड होना चाहिए था।
नहीं नहीं नहीं, see
अच्छा,
that's just a coincidence, that's all.
ओके ओके ओके
uh,
सर,
because I had arranged them in ascending order, so obviously this value is going to be lesser than this value, right?
ओके।
Similarly, this value is going to be lesser than this value,
Is
and
it not
similarly,
compulsory,
no no
which
no, it's not
which
compulsory.
I'm assuming, sir?
No no, you are trying to create a, I think you are trying to create a binary search tree, but we are
Like
not
that,
creating
sir.
a binary search tree.
Okay,
We are,
okay,
this is a binary tree. Binary search tree is a different thing. You can
okay,
create
okay,
trees in any manner, and Huffman creates the this thing in, this is the optimal merge pattern.
okay, sir.
So okay, it's not following BST rules.
Okay, okay. Thank you so much, sir.
Welcome. Okay, so this was about your variable length coding and uh, fixed length Huffman coding. I hope you guys understood what it is, and I hope you will be able to solve this question in your paper as well, right? Um, okay, so Huffman coding is done. Mhm. As you can see, this they have given you letters and frequency. You have to create the what do you say, the code. Okay. As you can see, there are how many codes are there? A, B, C, D is there's 7. So you are going to, in fixed length coding, you are going to take 3 bits, and in variable length also there's going to be 7 bits. I think, yeah, it's going to be 3 bits because 7, right? Nah, one of the characters might be 1 or 2 bit less. Try it out on your own, or should I do it here? Will you be able to do this, or should I demonstrate this one as well?
We will do it our own, sir.
Okay, okay. All right. After that, you have some divide and conquer ones. I will provide
Sir,
you
in
the,
examination, we have to also write the program for the to implement this because it's written
yeah,
somewhere
yeah,
that.
yeah. You have to
uh,
write this one as well.
okay,
And I I might have the code for this one. I will look into my folders and provide you guys the code. Okay. But yeah, you can also in exam, I think in your practical exam, you will, if you are not able to write the code, you can just you can just solve it theoretically.
okay, sir.
Okay,
Okay, right.
like we did here.
And this program will be written in C only, sir.
Yeah, yeah, all the
Okay,
questions for your DA should be done in C.
yeah.
Okay,
Thank you, sir.
think it is mentioned something, it's not. Okay, anyway. All right, next we have divide and conquer techniques, and this was Huffman coding algorithm. Next we have divide and conquer, in which you have binary search, merge sort, quick sort algorithms. Okay, binary search. Do you guys know binary search? What is binary search? Okay, before jumping into binary search, let's talk about what is divide and conquer approach. Right. See, I'm focusing more on the theoretical part because that's the important one. Practical exam तो निकल जाते हैं. The theoretical ones are the tough ones, right? So your theory should be strong. Yeah, divide and conquer. Very, yeah, divide and conquer strategy. What is divide and conquer strategy? We have all applied it in our lives in one way or another. And we are even doing it right now, aren't we? We are studying session by session. We are studying one section first, and after understanding that fully, we are moving to the next one. In Huffman coding also, I first told you about what is ASCII code, because before knowing ASCII code, if I started saying that, yeah, you have to do it 001 because of 3, convert it into 3 bits from 8 bits to 3, why should we do that, right? You should know that part, that why we are converting from 8 bits to 3 bits, or what's the reasoning behind that. Similarly, in divide and conquer also, first we divide that problem into small portions, into portions such that they are solvable, into portions that are understood by us. Okay. And in this approach, computer is doing the divide. So the problem should be understood by the computer. After divided into multiple parts, the computer must know what to do. Okay. And conquering means once you have conquered one, once you have solved one problem after dividing into smaller parts, you can move to the next one, solve that one, divide it, solve it, then move to the next one, and so on. So piece by piece, you are going to, first of all, first there's a big problem, divide it into small parts, solve one part, go to the next one, solve that, go to the next one, solve that one, go to the next one, and so on. That's the strategy of divide and conquer. Now let's take an example. You guys know what factorial is? If I say what is 2 factorial, it's 2 into 1, which is just 2. What is 5 factorial? It's 5
1 to
into
5.
5
3
into
into
4 into 3 into 2 into 1.
yeah, 120. If I ask you what is 0 factorial,
It's a 1.
it's 1. That's it.
1, yes, sir.
Now to find out minus 1 factorial, that cannot be done with normal arithmetics. We will need to use higher order mathematics. So that's out of our scope. So we can see that we have reached a solution a problem that we can solve ourselves. What is that? If I create factorial as a function f of n, then I have two answers. The first one is, see, if I write 4 factorial, what is that? It's basically 4 into 3 factorial. If you solve it further, 4 into 3 factorial is what? 3 into 2 factorial. And then 4 into 3 into, what is 2? 2 into 1 factorial. And finally, 4 into 3 into 2 into 1 into 0 factorial. Now 0 factorial we know, so we can solve it. We can go one step back, then we can solve this one, then we can solve this one and this one. Okay. So we are going to divide it into smaller parts. How we are going to do that? Let's see. It's in our mathematical definition itself. That f of n is equal to 1 if the value of n is 0. Yes. If the value of n is 0, if I'm trying to find 0 factorial, then the answer is 1. It's defined. It's known. But if I'm finding anything else, number that is greater than 0, for numbers greater than 0, what is it? It's n times f of n minus 1, right? N factorial is equal to n times n minus 1 factorial. Like 4 factorial is equal to 4 times 4 minus 1 factorial, which is 3 factorial. Now, if we don't know what 3 factorial is, 3 factorial is equal to 3 into 2 factorial. What is 2 factorial? 2 factorial is 2 into 1 factorial. What is 1 factorial? 1 into 0 factorial. 0 we know. Okay. So this is recursion. Whenever you think of, whenever there's divide and conquer, there's recursion. They go hand in hand. Okay. Now, this condition, the first condition, the value of which we know, this value, this thing, this is a solid number that we know. This is a variable. These are variables. What is it doing? I called a function and it called itself again. That's not an answer. That's like saying I'm asking you something and you're asking your friend, and that friend is asking some other friend. So I'm not getting an answer. Now I'm getting a reference to your friends of friends of friends. That's not what I want. If I've called you, you should give me the answer. Okay. So the solid answer is received when n is equal to 0. And that condition is called the base condition. Okay. So every recursion should have a base condition, because without base condition, the program will go into an infinite spiral and it will overflow. You will reach stack overflow. What is stack overflow? Whenever you call a function, there's something called a call stack. The call stack places your functions one upon above each other. So for example, if you have a main function, have you ever wondered that when you write a main function in C, you have written one line here, you have called printf function to do something, then you have called scanf function to do something, then you have done some arithmetic, 2 plus 3 something, and then you have returned. Okay. Have you ever wondered that when your program starts, it starts from the main function, correct? That's the entry point. So main function goes in first. Next, it calls printf. Now printf function is not written inside your code. It's written somewhere else. It's in the stdio.header file. Hai na? So it's going there. So the control from here goes to that code. It's executing that memory location. This memory location is different. This memory location is different. That memory location is for printf function. And this memory location is for your functions. So it went there, it did its job, and after completing it, how does it know where to return? And that's where call stack comes in. When you are in the main function, when you have called printf, it creates another section where printf function executes. Once it's done, the stack pointer is pointing to the printf function. Once it's completed, it will be deleted, popped out, and when you pop a function, you go back to the previous value. When you pop a stack, you go to the top of the what becomes the top? The one below the top, previously top value. Then you call the scanf function. So again, scanf function comes here and your pointer is pointing here. Once scanf is done, it again goes back to this one. So it knows where to return to. Okay. So if you don't know, if you don't have a base condition, what's going to happen? Your function will go into an infinite spiral. It will keep on calling itself. Okay, if I didn't know about at n equal to 0 it becomes 1, what I'm going to do? I'm going to calculate 0 factorial as well. 0 into minus 1 factorial. What is minus 1 factorial? Minus 1 factorial must be equal to minus 1 into minus 2 factorial. This is how it's going to keep on going, and this is going to go on for infinite, or until it hits an overflow. Overflow occurs when your stack, when you go beyond your stack allocated stack memory, right? So base condition is very important in recursive programs. What is the recursive program for this one? You have a function that returns an integer value, factorial, takes in an integer value of n, and it checks if n is equal to 0, then it's going to return 1, else it's going to return n times fact of n minus 1. That's it. Your base condition and your otherwise condition. That's it. That's recursion. Okay, that's divide and conquer. You're dividing a problem into sub problems, smaller problems that you can solve eventually. And in here, you have an example of binary search. There's something called a linear search and another thing called a binary search. And both have their own applications, where one should be used, where the other is used. Suppose I have given you an array, and it works on array only. I've given you an array with values 10, 8, 2, 5, 9, 70, and I want you to find a key value. Let's say the key value is 5. Okay. And this is your array A. What you're going to do in linear search, what we do is we scan it from this direction. So compare it with key. Is it 5? No. Is it 5? No. Is it 5? No. Is it 5? Yes. So after fourth comparison, we will get the answer. But if it's something like 55, then again no, no, no. So after doing 6 comparison or n number of comparisons, right, we will go to the end of the array and we will know that the element is not there. So the complexity of linear search is O of n. Best case is O of 1. If you are searching for 10, then the first element will give you 10. That's it, done. And average case and worst case are O of n. Uh, Worst case is O of n. Best case is 1. And average case is also n. Because by average, what is going to be? It's going to be this character, this one, this one. It's still doing some research now. And where is linear search used?
Sir, sorry for interruption, sir. How can, sir, average case will be big of n, sir? Big
Okay.
O of n?
Yeah. See, if you have elements, say there are 1,000 elements. Okay. From 0 to 1,000, there's an array containing 0, 1, 2, 3, 1,000. Okay.
Yes, sir.
And you want to search for the, say, 980th element. So after doing 980 comparisons, you will find that array, find that
Yes, sir.
value. Suppose you are searching for 400, 400 character. So you will do 400 comparisons and then you will find it.
Yes, sir.
So does it matter that you are doing n comparisons or n by 2 comparisons? Does it even make any sense? Because let's say you are searching for the third element. That's the best case scenario, but that's still not the best case because it's doing 3 comparisons.
Yes, sir.
But if you are searching for 980th element, then you are searching n minus 20 times. So you are
Yes, sir.
going to n, right? Towards the
Yes.
end of the line, and then you are finding it. So if I say n by 2, that also doesn't make any sense. So worst case and best average case is usually taken as the whatever is the worst case.
Okay.
Because by
Thank you, sir.
even no one is looking for the average case. You either go in full with the data or you go with the your best case scenario. right?
Okay.
So usually
Okay.
you are
Thank you.
only left with the average cases comes out to be your uh, same as the worst case. And again, in asymptotic notations, we don't factor in what you say exponent.
Sir, we
Sorry.
took a
Hmm?
asymptotic notation, में, sir. We take only the degree of the function. Am I right, sir?
Yeah, yeah. You take the highest degree,
Function. Highest degree. Yes, yes,
highest
sir.
degree of the function,
Okay.
and
So here in the both the case, sir, highest degree will be one, sir. So that's why we took a big of n in both average case and worst case.
yeah, correct. But I think
Okay.
you are missing the point a little bit here.
Yes,
Uh,
sir. What, sir?
yeah. Let me. I always do this exam exercise. Suppose I have given you n equal to. You are taking that from user. Okay. You are taking
Okay.
some n value use from user. You are scanning scanf n whatever you do. You're taking some value from user. Suppose the user has supplied you with 5, and what you have
Okay.
to do is simply just do, you have to give the sum of the natural numbers till that number. So you have
Okay.
to simply do 1 plus 2 plus 3 plus 4
Four,
plus
five.
5 and give
Yes,
it
sir.
back to the user. That's it. What is the strategy that you are going to use? How we can get there? I can also do something like this: 5 plus 4 plus 3 plus 2 plus 1. That's it,
Yes, sir.
right? I can do anything. I'm just, what's the first thing? I can use loops here.
Yes,
Can
sir.
I? Yeah, you can use loop. Suppose your n is this thing. I'm going to create a variable called sum, and it's going to contain 0 initially. Then I'm going to loop. I'm going to loop from I is equal to 1 to n. And what I'm going to do is I'm just going to simply do sum is equal to sum plus I. So what's going to happen here? This sum value is first 0, then I value is first 1, so it becomes 1. So sum is converted to becomes 1. Next time I becomes 2. I was first 1, now it becomes 2. So 1 plus 2, sum becomes 3.
Three.
Then I becomes 3. Then we have 3 plus 3. So sum becomes 6 and I becomes 4. Then we have 6 plus 4. So sum becomes 10 and then I becomes 5. Then we have, sorry, this becomes 10 plus 5. So sum becomes 15. I becomes 6. It goes out of the range. It goes out of the range. So we stop this and we have found our answer to be 15, right?
Yes, sir.
Okay. Let's do the time complexity analysis of this algorithm. When we say time complexity analysis, see, it it refers to how much time it will take the computer to perform this, the CPU to perform this. There's something called a constant time, and then there's something called a variable time.
Yes, sir.
What is constant time? Constant time is that operation that is
Perform only once.
defined, not performed only once.
Okay.
Something which is defined in the compiler itself, sorry, in the CPU itself. All the ALU work is
Yes.
constant time. It's
Okay.
represented with O of 1, but you can represent it with O of 100 as well. This is also constant. Constants are what? 10, 20, 100, 40, 50. These are constant values, discrete values, numbers. Once I say O of n, n is a variable. So that becomes variable time complexity. Okay.
Okay.
So constant time is just, we just represent it with O of 1. That's it. So arithmetic and logical unit ka jitna bhi kaam, all the work that ALU does. What does the ALU do? It does
Arithmetic logic units, a basic operation like addition, subtraction, multiplication, division,
exactly,
and
as well
yes,
as logical work, that is
as a
comparing, right, equal
okay.
to. And if you take into consideration the input, also ALU works are constant time. Similarly, all the input output operations are also constant time.
Okay.
These are defined in the CPU itself, that this operation will take this amount of work, like this amount of time it will take to complete it. It's already defined in the CPU itself. So those things are called constant time. So
Okay.
if we look into this into our algorithm from one by one, let's see. This is my first line. This thing. This is input.
Yes, sir.
So by definition, it should take O of one time.
One time. Yes, sir.
Next is this one. This is the work of ALU, because you are assigning something to something.
Okay.
Assignment works.
Yes, sir.
Assignment works is
Assignment.
also for ALU. If you have studied assembly, there's something called the MOV mnemonic, which is used to move value from somewhere to a register. Okay, so that thing is also done in arithmetic and logic unit. So this is also going to take O of one time.
Yes, sir.
Next up, let's look at this line. Here, what we are doing, this is arithmetic and logic unit.
Yes, sir.
We are doing arithmetics. So this is also going to take n time. If you look at this expression, like there's going to be an expression like I should be less than equal to n. This condition is being checked rigorously, right? We are checking it
Okay.
continuously that whether it's true or not. So how many times is this being checked?
So loop will be check n plus one time, sir.
N plus 1 times, because by n times it will reach there and then it will perform the 6 is less than 5. This will be my sixth comparison. So that is n plus 1. If your n is 5, it will do 1 is less than 5, true. 2 is less than 5, true. 3 is less than 5, true. 4, 5, true, true. No, sorry. Yeah, equal to, right? Less than equal to, less than equal to, less than equal to, less than equal to. And on the sixth try, it will yield false and it will be done.
Yes, sir.
So that means that how many times as this statement is going to run?
The statement
5
will be
times.
run, sir, n times, sir.
N times, right? 5 times
Yes,
it
sir.
will run.
Yes, sir.
It
So
is run up to 5 times now, because for n you have declared a very constant
exactly,
value, you have declared 5.
exactly. If I'm
State,
taking
That's
it
why
as
the
n
loop
is
is
equal to 5.
continue up to 5 times,
Yeah,
no,
from
exactly.
0
loop
to
will
5.
be executed, sir. A loop will be executed n plus one time, and the statement will be executed only n times. क्योंकि
See,
n
in
plus
No,
the
but
one
loop,
term,
we have
it
already
it
declared for loop, we have already declared that value now for n equal to 5.
yeah. See, another thing that you have to understand that this value is a input. It's not constant. This value is coming from user, so user can input 5, it can user can input 10, it can user can input 100,000. It's up to the user, right? So this becomes variable, even though the operation when you are taking in that variable, that's taking O of 1 times, right? But the value can differ, and here it's going to this line of code is going to run n number of times. This it takes one constant unit of time to do this, but this thing is going to run n times. If the n is 5, then it's going to run 5 times. If it's 10, it's going to run 10 times. If it's 1000, it's going to run 1000 times. Now here's the twist. Suppose that O of 1 is 1 second. So therefore input will take 1 second of time. This assignment is going to take 1 second of time, and each statement in here is going to take 1 second of time, but this is going to run 5 times. So total it's going to take 5 seconds. Or if it's going to run n times, then it's going to take n number of seconds. Okay.
yes, sir.
Yeah. So if it's going to run n number of times, so if the value of n is 5, then it's going to take 5 seconds. We are happy. If the value of n is 1 million, Then how many times are we going to wait here? 1 million seconds. 1 million second is what? Let's calculate. What is 1 million second? $11. We are going to wait for 11 days. Right? That's okay. That's I'm just trying to explain you the absurdity of it. Of course, it's not going to take 1 second for each instruction. It's going to take some nanoseconds. But I'm just trying to make you understand the bigger picture, right? So if here, what's happening is input is taking one time. This assignment unit is taking constant time. This loop, this thing is taking n time. So it's taking 2 plus n, and this is noted in the O notation. And in O notation, we get rid of the constants and coefficient terms. So we are left with O of n. Okay. So this notation implies that this function, whatever the program that you have written, is going to run linearly. It's running on a linear time complexity, meaning as the input size increases, the running time complexity will also increase. The runtime will also increase. Okay. So the n variable came in. Why? Why did the n came? What was the reason? See, before a loop, everything was fine. Once we introduce loop, it brought in n, because we have specified that loop is going to run n number of times. So because of loops, variable time complexity comes into play. Okay. Now, if I ask you, can you convert this? Can you give me an algorithm that can do the same operation but in constant time? Basically, you have to take input from user, set sum is equal to 0, and then you have to not use loop. Without using loop, you have to convert this into a O of 1 time complexity. Can anyone give me an answer for that? How you are going to convert this?
Sir, could you please repeat?
Yeah, I was asking ki, this algorithm is taking O of n times, right? Because of the loop. Because of the loop, it's taking n times to complete this procedure. What I want is, I want to get rid of this thing, and I want to do it in constant time. I don't want to do this in O of n. I want to do this in O of 1 time. How I'm going to achieve that?
So here that time we have declared that value that n equal to 1.
Hmm.
So first it will take 0 of 0, then it will take of 1.
No. How?
Can we use recurrence, sir?
Yeah, if recurrence, no. See,
Sir,
hmm,
can I use formula, sir?
of course, of course.
Yeah,
What
yeah,
you're going?
correct.
What's the formula you are going to use?
N
Sir,
in
n into n plus 1 by 2, sir.
Why should we use that formula?
Uh,
is
because, sir,
AP.
Yeah.
yes, sir.
No. Continue. Why should we use that formula?
Because, sir, we are finding the sum of n natural numbers, sir. That's why we
Yeah.
can use the formula where we can get the answer of n natural numbers, sir. Sum of n natural number.
Exactly. If I'm doing 1 plus 2 plus 3 plus dot to n number of times, this is basically what? S of n. If you have studied AP, arithmetic progression,
Yes, sir.
to find sum of n natural numbers, there's a simple formula. N by 2, n plus L. Not n plus L, A plus L. Where n stands for the number of terms, A is the first term, L is the last term, right? So for n equal to 5, we have 1 plus 2 plus dot 5. So sum of 5 natural numbers is equal to 5 by 2 times a, which is 1, plus last term, which is 5, and this comes out to be 15, right? 3, 5 3s are 15. Now let's apply the same formula here. N is given by the user, divide by 2, okay? Multiply with a. What is a? First number. What is the first number of a natural number?
1, sir.
1. So it's 1 plus what is the last term?
N, sir.
N, because if I'm doing 1 n is equal to 5, so that's 5 is going to be my last term.
Yes,
So
sir.
we are left with this formula, n times 1 plus n plus 1 divided by 2. So what I can do is, let me write it again here. We are taking n as input from user. Then we are declaring sum is equal to n divided by 2 multiplied by n plus 1. Done. Arithmetic is going to take constant time. Division is going to take constant time. Multiplication is going to take constant time. All in all, this is going to take constant time. This is taking constant time. So this is going to be solved in constant amount of time. So even if you put 1 million here, it's going to be solved instantly. So that's the difference. That's the analysis of an algorithm. Design and analysis. DA, right? Design and analysis of algorithm. We are finding algorithms and we are checking it and we are analyzing them. Both are doing the same thing. The first one is also finding the sum of the natural numbers. The second one is also finding the sum of the natural numbers. But the way they are doing it, there's some difference. Okay. So the time complexity arises because of loops, because of recursions. Okay. If I ask you to do something and you ask someone else to do it, and that person asks someone else to do it, and that person asks someone else to do it, then you are infinitely waiting, na? But if I ask you to do something and you do it right there, then and there, then you are doing it constant time.
Sir, uh,
Yeah.
when I will use the formula, sir, then for big of O or theta of O or delta of O, omega of O, सब
Yeah.
तो सर वन ही होगा सर.
Yeah. All of these are going to be one for
Best
this
case, average case, and
algorithm.
worst case.
Yeah. Best case, worst case, all are one.
All these are ones. Okay.
Yeah. Another
Sir, so
thing is,
this one is better than the better than using the iterative sir, iterative loop, sir.
see, if you have the option to go to skip loops, if you
Okay.
have, if you can see the pattern, see, that's why I asked the question in the first place. And when I said that you can use loops, everyone jumped in on that. No one
Yes,
said
sir.
that I can use summation also, right?
Okay.
So we always as humans we are going to fall with the whatever method comes to first comes to mind, right?
Yes,
So
sir. Yes.
loops comes naturally to us that okay, we can loop it and get the answer. But once we go into a little bit more study of it, once we do some more research into it, we can find some intuitive ways. We can convert it into O of one. We found it. And similarly, when in real life also, when you are doing you're developing a software, if you are stuck somewhere, if you see that okay, this is taking too much time, is there any way I can solve it in a faster way? Go to the community, go to Stack Overflow, go to a Discord server, go to someone, go to a teacher, ask them. Okay. Because
Okay.
obviously research and development, they go hand in hand, right? Development can happen if there's research, and research happens if there's development.
A lot of
So
thanks, sir.
welcome. So my point was this, that loops bring complexity. So if you have a single for loop, I equal to 0, I less than n, I plus plus, and suppose it's doing some statement, there's some lines of statements going on, this is going to repeat n number of times. But suppose now this whole thing is also a part of n, it's also a part of a loop for j equal to 0, j less than n, j plus plus. Now this statement is going to repeat n number of times. So ultimately this statement is repeating how many times? It will repeat n number of times inside this loop, and this loop itself is repeating n number of times. So it's going to be 1 into n into n. So 1 into n into n. So that's n square. The more nesting you have inside a loop, the bigger the complexity is going to be. And we always take the higher order one. There's a reason. If I have 5n square plus 3n and I am representing it with O, this is going to become O of n square. The reason is, take an analogy. Suppose you have from the ocean, you add 4 buckets of water. You added 4 buckets of water. Did anything change? Was
नो
there a
सर,
tsunami? Was there a tide? No, nothing
नो,
happened.
बहुत ज्यादा
Right?
फर्क नहीं है कुछ.
Bilkul. So there was no difference. There was no significant difference. So ultimately, I can just go with this, that the ocean level is still the same. It didn't change anything. Similarly, if I take out something, if I minus 4 buckets, that's also not going to affect me in any way. Right?
Okay,
So
that's
that's
why,
why,
sir.
yeah, that's why we always go with the higher order notation. And another reason is, suppose, and this is only true when, see, n value is very, very large. N value should be very, very large. We don't consider it for smaller values. Okay.
Okay.
There's a graph you will see uh, when you are studying complexities. It's something goes like this, that if it's C of G of n, this is f of n.
And yes, sir.
So it's saying that, look at this portion. At this portion, the values are fluctuating. But after this particular point, f of n is always greater than this value.
C of
Exactly.
CG. Yes, sir.
So this value is giving you the best case. This is omega. And if
Okay.
it goes beyond that, if you have another, say, e
Worst case.
times, yeah, e times g of n, this is your worst case. That after this particular point, this is the value of n only. That after this particular value of n, the functions are going to go like this. This is going to be the best case, and this is going to be the worst case, and this is your average case. Okay, it shows growth. If you take an example, say I take n is equal to 1000. Okay, so if I solve it, what is going to be 5 times 1000 square is
10,
this,
10 lakhs, sir.
yeah, and then 3 times 1000, which is larger. If you
Which one?
have, let's say you have 50 lakhs.
Yes,
Okay,
sir.
if you have 50 lakh money and someone gives you 3000, or someone takes away 3000, does it affect you? Not drastically, right?
Yes,
If
sir.
someone gives you even 3000 rupees, you're still fine. You still have 50 lakh rupees. It doesn't matter much. So you see, the value of n will dictate who is the dominating one. This term is the dominating figure. This is not the dominating figure. Okay. On one side you have 50 lakh, and on the other side you have 3000. That's the difference. Okay. So that's why we always take the higher order function, higher degree function, sorry. Yeah, and I was talking about linear search, right? See, linear search is used when your program is, when I have given, suppose I have given you a deck of card. Okay, I've shuffled the deck of card. I have given you, and I want you to find me the spade of, let's say, 4 of spade. Okay, so how you are going to search it? Do you already know the location where it's going to be, or you are going to search it one by one? One by one.
Search it one by one, sir.
Exactly, because you don't know the location, right? I have shuffled it.
Yes, sir.
So when you have shuffled data, when the data is out of order, you can use linear search. But when you have a when you have a sorted list of data, suppose I have given you a book. Okay, let's take this book itself. There are 56 pages here, right? I want to go to page number 25. Am I going to go like this? Am I going to do, okay, this is not it, this is not it, this is not it, this is, am I going to do that? No. What I'm going to do, I'm going to directly go somewhere in the middle, and I see, oh, I'm at 21, so it should be over here somewhere. Okay, and I found it, right? I will go something like this. If I given you a book and I want you to open and say there's 100 pages, I want you to open page number 70. What you're going to do? Are you going to turn it one by one page at a time? No, you're just going to open it in the middle and then look at the page number. If the page number is 60, then you are going to continue searching in the right hand side. You don't care about the left hand side data, right? Because you are searching for 75. 75 is obviously not going to be on the left hand side of the book, right?
Yes, sir.
Yeah. So if you have a book and there's 0 to 100 pages, and after opening it to the middle, you find that this page is number 60, then you don't care about these pages. You are going to search in the 60 to 100 range. You are going to find their middle value and you are going to search there again. Then again middle value, again middle value. And this is the concept of binary search. This is the concept of divide and conquer technique used in binary search. Divide the array, find the middle element. If the middle element is the element you are looking for, well and good, return. But if it's not the element, check. If the key you are searching for is less than this, if suppose where's my pen? uh, yeah, suppose the key you are searching for is 20. 20 is less than the mid value. The mid value is 60. Okay, if the key value is less than mid, then obviously it's on the left hand side, so continue searching on the left hand side. But if the value is greater than mid, then search on the right hand side. Okay, that's the concept of binary search. And for binary search to work, you need sorted data. Otherwise, you cannot do anything with it. So suppose I have here 20, 35, 60, 89, 116, 200. And I'm searching for the key value, say 116. Then what I'm going to do is 0, 1, 2, 3, 4, 5. This is your array A. We are going to find the mid value. What is the mid element? Mid element is found by taking the floor division of L plus H divided by 2. This is your low, this is your high. Okay, lowest page number, highest page number. And you divide it by 5 and get the floor value. What is the floor value? When you divide something, you get, suppose you are dividing, you have 4.5. When you are rounding it off, you will go to the next integer, closest integer, right? And it will become 5. But when we are talking about floor value means, see, on the left hand side, you have here, you have 4 on the number line. Imagine it on the number line. There we have 4, here we have 5, in between you have 4.5. When we are talking about floor value, you look for the nearest integer on the left hand side. On the left hand side, it's 4, so the floor value is 4. And there's something called a ceiling value. It's represented by this 4.5. Ceiling value means whatever the value I have landed on, go to the right hand side till you reach the nearest integer. So the nearest integer to the right is 5. So this value is 5. Okay. So here we do floor division. So floor division of this, what we are going to get here, mid value is going to be, M is going to be 0 plus 5 by 2, that is 2.5, but we are going to only take 2, so 2. So this is your mid element. Now compare it. First of all, compare that A of mid is equal to key. Is it? No, it's not. Then what should we do? We should compare whether A of mid is greater than key. Is it greater than key? Is 60 greater than 116? No. then the last option is this less than key? Is mid value less than key? Yes, it is. Therefore, my key value should be on the right hand side. Or you can imagine it like this. Let's think of it like this. Is the value of key, whatever the value you are searching for, is it greater than whatever you have found? Yes, key value is 116 and it's greater than the mid value. So obviously it's going to be on the greater sign. What is the greater sign? Right hand side. So next up, we are going to search in this bracket only. We are going to search for 89, 116 and 200. Here we have 3, 4, 5. Why didn't we take 60 here? Because we already compared it, na? We already compared this. So we don't need to compare it again. Now find the mid value again. Here L is 3, H is 5. So mid becomes 3 plus 5 by 2, which is 4. 8 by 2, 4. So your mid value comes out to be this. And if you look, yes, this is the correct one. You have found the answer. So go back and it's done. Okay. But if you are searching for, say, 160, 1160, then whatever the value I have found, is it equal to the key value? No. So the condition is false. Next, is the key value greater than mid value? Yes, it is. Key value is greater than this. So we have to search on the right hand side again, on this side. And here we have only 200 with 5. This is my L and this is my H only. Mid value is going to be 5 plus 5 divided by 2, which is going to be 5. So my mid value is also this. Is this the key? No, it's not. If it's not the case, is the value greater than 200? Mid value? Yes, it is. So go to the right hand side. But if once you go on the right hand side, what happens? If you look at here, your L value was updated to here, right? See, it came here. And then again, it was updated to here. It was updated to here. So L is going to be updated to mid plus 1 again, right? This was mid. Mid plus 1 is this value. So what we are doing here is, if the key value is more than this, we update our lower page to mid plus 1. Else, we update our higher page to mid minus 1. Okay. Let's say if you are searching for, instead of 1160, you are searching for you are searching for, say, 70. So 70 is greater than 60, so we came this side. Mid value is 116, so we should travel on this side. So H becomes this value. So we are at 89. This is 3. This is my L. This is my H. And this is going to be my M value as well. And M is not here. So we have to search this side. And this side, there's no element. So we have to return. So we can say that no element has been found. And if you look at this, how many comparisons did we do for 70? 1, 2, 3. After 3 comparisons, our answer is clear that the key is not there. But if we were searching, if we did linear search on this, what would we have to do? Comparison 1, 2, 3, 4, 5, 6. So after 6 comparisons, we will know that the key is not present. So binary search divides the problem and then looks for the solution. Okay. Think of it like this. If this is your book, right? You have opened the book. Initially, you had page number 0 to 200 and you had opened between, let's say, 100. And you are searching for page number 156. So your next, what is going to be your next low? This was your low. This was your high. Your next low is going to be 101, right? From 101 to 200, you are going to search. So this was your mid element and you are searching for mid plus 1. Okay. Similarly, suppose the number you are searching for is sorry, where is it? If you are searching for 57, then this value is what? Less than mid value. So you have to search this side. So you have to search from 0 to 99, right? You are getting rid of this portion. So you updated your high value. So if your key is less than whatever the mid has found, you have to update your head. You have to update your higher value. But if the value is greater, then you have to update your lower value. You're adjusting the pages basically. Okay. So merge sort is based on binary search is based on that idea. Clear?
Yes, sir.
Okay. Binary search is done. There's also merge sort and quick sort that's left. Okay. Have you guys done merge sort or quick sort? Because I think
Yes, sir.
you have done it. Okay.
In algorithm classes, we have done.
Okay.
Yeah.
Okay. Wait a minute. Let me just check one thing. Um. What about Dijkstra's algorithm? Completed Dijkstra's algorithm?
नहीं सर, करवाना है सर.
Dijkstra.
That's नहीं हुआ है.
Okay, let's complete Dijkstra first because I think only 1 hour left. If time is there, you can just select one of these two, whatever you are having doubts with. If you have any doubts with merge sort or quick sort, we can discuss it later on. Okay. Let's quickly finish up single source shortest path algorithm. We have Dijkstra's algorithm, a very simple algorithm. Mm, mhm. Yeah. So we have okay. This problem comes under SSSP problems, which stands for single source shortest path. Okay. And in here we have Dijkstra's algorithm. How do you pronounce it? Dijkstra. Okay. Dijkstra's algorithm. Dijkstra's algorithm. Okay. What is single source shortest path? So the name itself is saying that there's going to be a single source. So from one source, you have to find the shortest path to all the vertices. I hope you are familiar with the graph terminologies, like what is a vertex, what are vertices, what are edges. No.
Yes sir, yes sir, we are familiar sir.
All right. Then let's take a simple example. If you have a vertex, say A, from then we goes to B, then there's C, there's something called a D. D comes from like this. And yeah, let's take this example first. It's 2, 3, 5, 9. Okay, and we are going. Acha, from every time there's a question regarding single shortest path. There's another thing called all pair shortest path. that that means you have to find the shortest path between all the vertices. So basically, Dijkstra's algorithm applied multiple times, n number of times, whatever the number of nodes are. Vertices are, sorry, v number of times. So but in single source you will only have one source vertex. So let's say A is your source vertex. From A we have to find our shortest path to all the other vertices. And here comes a concept called relaxation. Okay, when we talk about relaxation means we relax an edge. Okay, so how do we relax an edge? Relax from U to V. What is U? U is your starting vertex, and V is your final vertex. So if you want to go from A to B, A becomes your initial vertex, B becomes your final vertex. Okay. Just like in physics also, we study, right? Final velocity, initial velocity represented with U and V. Here, vertices are also represented with U and V.
सर एक क्वेश्चन था सर, ये मिनिमम स्पैनिंग ट्री से कैसे डिफरेंस होता है, क्योंकि उसमें भी हम लोग मिनिमम कॉस्ट को फाइंड आउट करते हैं.
Yeah, see, minimum cost is a different thing. In minimum cost spanning tree, when we create a the goal of it is to create a tree, and a such of a tree which has the minimum cost. What does that mean? When you have a graphs, uh, what is the difference between a graph and a tree? See, trees are also graph.
Yeah.
Yeah. So what's the difference?
It doesn't contain cycle, sir.
Yes,
That's the one
tree
thing.
does not contain any cycle, and there's a pattern. You will see that if you have a tree, say this thing, or let's say a tertiary tree, or say here, how many vertices are there? 3.
3,
How many edges are there?
2,
How many vertices are there?
4,
How many edges?
3,
How many vertices?
4,
How many edges?
3.
3. If I increase another one, the number of vertices becomes 5 and edges
Yeah,
becomes 4.
yeah,
So there's a relation between the number of vertices and number of edges. If
yeah,
there are if there are n number of vertices, then the edges should always be n minus 1.
yeah. Correct, sir.
So that's another condition for something to be a tree, for a graph to be a tree. And yeah, minimum cost spanning tree, what we are finding out is, see, if you have a if you follow Kruskal's algorithm when finding minimum cost spanning tree, you might encounter, you might develop a discontinuous tree or mm, unconnected tree,
Yeah,
right?
correct, sir.
Because it takes the minimum values first, so obviously
Mm,
it will end up with a, it will start with a disconnected tree.
yeah,
But when we are talking about Dijkstra's algorithm, it's trying to find the shortest distance from a single source. See, in MCST, in Prim's algorithms, the source vertex is very important, because
yeah,
if you take a vertex, oh, sorry, if you take a vertex which only has incoming edges and no outgoing edges, if you take this as a starting vertex, then you are going to end up with just this. This is going to be your MCST,
yeah, yeah.
correct? So
Correct.
in MCST, your source vertex is dependent in such a way to create a tree that could encompass all the vertices, and as well as create a tree and
Yeah,
follow and create a minimum, and should have a minimum cost. But when we
yeah,
are talking about Dijkstra's algorithm, we are only interested in that from this starting vertex, whether I can go to all the other vertex or not, and if yes, then what is the cost that is required.
yeah,
So if you take an exam, see, when you are finding MCST, MCST only takes will find you the shortest path. Not the, it's not finding the shortest path. It's just creating something. That's it. Okay.
So if you assign the distance, sir, again, it's finding the minimum distance path from one node to the rest of the other node. Just
Yeah.
that's why I
Yeah.
got confused with Dastra and all this.
Yeah. See, when you are searching for in MCST, there could be a chance. Say, suppose you have something like this. Okay. T. Now, if uh, 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 uh,
Sir, sorry for interruption, sir.
yes, yes, go on.
Sir, in minimum spanning tree, sir, the definition of minimum spanning tree is all vertices are included and the number of edges will be one less than the number of the vertices.
Yeah.
And this concept is already used in the Discastra algorithm. So how it is different from the minimum spanning tree, sir?
Okay. See, I have created a simple tree here. Okay. A, B, C, D. Okay. Let's say that A is my starting vertex and I want to create a MCST. I'm going to follow Kruskal's algorithm. You can follow your own. Okay. So I have from B to C, I will take first. Then I will take A to D. And then I will take A to C. And that's it. We are done. Right. So this is my starting vertex. And from starting vertex, I can see to go here, I have only what? I have 2, I have 3, and I have 1. What is the total cost? 6. What is the information that I'm getting? That the total cost of this tree is 6. That's it. Is there any indication that for going from A to D is going to take 2?
No, no.
Do I know that? No, I don't know that. Do I know if I can go from A to B or not? Because it gave me a minimum cost. That's fine. But do I know whether I can go from A to B or not? Because you can see that B has no incoming edges.
Yeah,
So there's no way I can reach there. Correct.
correct.
So
But
MCST,
okay. So for directed graph, yeah, right. Yeah, got it. Little bit.
yeah, see, in real world also you will have directed graphs, right? Most of the time. If you take into consideration traffic, if you are going from one place to another, it's going to show you directions,
Yeah, yeah, right,
right?
sir.
And see, MCST is used. In Dijkstra, you can see the use of MCST, that it's taking the minimum path.
Yes,
But
sir.
Dijkstra's algorithm is doing something else. It's giving some different output, and MCST is giving you some different output.
नो सर बट सॉरी सर
Mhm.
बट मैंने जब एक क्वेश्चन पे निकाला था प्रीवियस ईयर सर दोनों से आंसर सर सेम आता है सर एक मैंने प्रिम से ट्राई किया था प्रिम से मैंने वो मिनिमम स्पैनिंग ट्री में मिनिमम कॉस्ट फाइंड किया था और
Uh,
डिस्कास्ट्रा से भी तो आंसर विल बी सेम सर आंसर वाज सेम सर
did you check it with all different graphs as well?
नो सर मैंने दूसरे ग्राफ पे नहीं देखा था उसमें था कि आप प्रिम्स में और डिस्कास्ट्रा में आपको दोनों से आपको फाइंड करना था एक क्वेश्चन था सर आई हैव डन इट सर आई विल सेंड यू ऑन योर व्हाट्सएप सर
Sure,
व्हाट्सएप
sure, sure.
Jafar, yeah, for directed graph, without undirected graph, I think it will be similar. But for directed graph, the challenge is whether we can go to the vertices
यस
or not. That's the only
Exactly.
difference I could guess.
And see, another thing is that again I will emphasize on this, that MCST is only giving you the minimum cost. That's it. It's not giving you anything else.
ओके
Dijkstra's algorithm gives you the path. Okay, we are interested in the path. If I want to travel from Delhi to Kolkata, then I need to select a train such that it's going to follow the minimum route, or it's going to follow some certain weights. The weight could be time, it could be money, it could be distance, right? Weights are
सर
just arbitrary some values.
ओके
If
सर
I'm
यू वांट टू से सर it give us minimum cost as well as sir the way how we can uh,
how we can travel there,
travel
we
there
can
how
get
can we
there.
reach at our destination sir
Yes, and another thing is,
yes sir
see, uh, if you have gotten the minimum cost, okay, once you have gotten the minimum cost, that minimum cost doesn't really make much sense, because that minimum cost is for the whole tree. Okay, but in Dijkstra's we are not eliminating edges, are we? No, we are not eliminating edges, we are just trying to find a path. from A to another vertex, from one vertex to all the other vertices. Okay, that's all we are trying to do. So in here, to find the algorithm, sorry, to solve it, I will explain the relaxation in a bit. Okay, let me just quickly do something here.
Sir, is this Castra work on, sir, negative weightage, sir?
It
Negative age
it
weight?
it will it will fail on negative edges.
How can we
For that,
find, sir? How can we find, sir, if question will ask in our
uh,
final examination? I have already seen one
see,
question, sir.
no. Dijkstra's algorithm is able to work on negative edges, but
Okay,
it is not able to detect negative edge cycle.
okay.
There's a difference. If there's a negative edge, it does not mean it's going to create a negative edge
Sir,
cycle.
suppose we have three age, we have 3 age, and weight of these 3 ages are 2, 3, and -1. So
Yeah,
which among these weightages, which one is, sir, smaller value?
obviously you are going to follow the minimum one. Yeah?
The minimum one is
Minimum
negative weightage is minimum or not?
negative weight is minimum, but there's one. Okay, look, we are not we are not interested in the weights that much. We are interested in how they are connected. Okay, Dijkstra is finding that connection.
Sir,
Suppose,
connection with the, sir, minimum cost, sir, na?
correct, minimum cost is there, but you are
Yes, sir.
trying to find the edge. Na, your connection is there, right?
Yes, sir. The connection in that way, sir. Suppose
Yeah,
we
yeah.
have 3 edges, sir. In your diagram, sir, in your figure, sir,
Mhm.
A, B, C. B is connected with three vertices, sir, A, D, and C. Suppose
Correct.
B to A, the cost of edge is 3, and B to C, the cost of edge is -9. Yes, sir. तो
B2C,
इसमें हम,
I'm taking
yes,
-30. Okay,
yes, sir, yes, sir, yes, sir.
all right.
Got it, sir.
Okay,
इसमें कैसे करेंगे?
all right. Let's see. Initially, when you are at index this, we assume that all from where you are standing, that position is
Zero,
cost is 0.
zero. Yes, sir.
And to go to all the other wedges, we assume them to be infinite. Suppose I'm
Infinite.
sitting at
Yes,
home, I don't know the what is the current rate for auto walas to go to some particular
okay.
location, then I'm going to assume it to be the highest number, right?
Yes,
Unless
sir.
I go there, I won't know. So after you start relaxing it, see, A can relax B, so it becomes that A to B I can go, and the cost is 10 rupees,
Yes, sir.
let's say. Okay, and afterwards I still don't know about C. I will know about it in the next run. Okay,
Okay.
in the next run, what happens is, this is A, this is B, this is 10, this is also 10, this is C. This becomes what? See, to
30.
go to C, I need to first go to B. So I spent 10 rupees. And then
Yes,
from
sir.
B to C, I spent 20 rupees more. So total it became
30.
30.
A to
So
C.
yeah, so it's become 30. And how I am deciding it again? Sorry, here we have 20. So, and here we have infinite. So I'm checking whether infinite, I'm taking the minimum of infinite and 10 plus 20. What is 10? This value. When
Yes,
I'm
sir.
at B, the value of that, what is the cost of reaching there, and the cost of traveling this distance. The cost of traveling this distance is 20. So the minimum of 30 and infinite is always 30. Okay, so I have decided, so I can decide that C value is going to be 30. Now let's relax it one more time. Okay, there's one edge left, let's do it again. Okay, let's see what we have. So I have A. From A we can go to B with cost 10. From B to C, I can go with cost 30. And from there, I have minus 30. So let's again check here. I'm relaxing this edge from C to B. Let's see. I have to take the minimum of 10 and what is? the value of this 30 plus the cost of going from C to B. The cost is minus 30. So this is going to be 10 comma 0. So that means I should take 0. So this is going
Yes.
to become 0. But Dijkstra has a condition. It says if you have already relaxed an edge, then you cannot relax it again. Okay. Bellman-Ford algorithm shines here. Bellman-Ford is able to detect this relaxation part. It becomes 0. Okay. Now let's see what's the cycle here is. Okay. Now, once it becomes 0, compare it. 0 plus 20 is 20. And the cost of reaching C is 30. So which is smaller? 20. So this becomes 20. Now, from 20 to C, from C to B, it's what? 20 minus 30 is minus 10. So from 0, it becomes minus 10. Then 20 becomes what? Minus 10 plus 20. It becomes
सर इस
10.
सर यहाँ तो नॉन टर्मिनेटिंग लूप बन गया सर.
Exactly. ये terminate नहीं होने वाला. This is going to keep on going forever. And why is it going to continue? Because there's a cycle. And this cycle is a negative edge cycle. That's why.
ओके.
That's the reason. But suppose suppose this value was not 30 and this was just 3. Okay, suppose it was 3, then what would happen? You have minimum of 10 comma 30 minus 3, so you have 10 comma 29, sorry,
27.
27, right? So minimum is still 10,
Yes sir.
so it's valid.
Okay.
Negative edge is there, a cycle we can see that there's going to be a cycle here, but did this edge create a cycle?
No.
It didn't create a cycle. But if the edge was of different value, it would have created a cycle.
Okay.
Okay. So Dijkstra algorithm is not able to catch these things. Okay. Dijkstra
So
says to
sometime it may work or sometime it may not
exactly,
work.
exactly.
Okay.
Sometimes it works, sometimes it does not work.
Okay.
Dijkstra algorithm is not capable of detecting negative edge cycle. In that regard, Bellman-Ford comes in, and Bellman-Ford algorithm is able to detect these negative edge cycles. Because it, after relaxing it, see, it relaxes it the v number of vertices number one number of times, so it will relax this graph 2 times. And if you look at this was my relaxation 1, this was my relaxation 2, and after these two relaxation I have achieved the correct graph, because afterwards the third relaxation is going to what, is going to create the cycles, right? This was 30, so this will become 0. So
Yes
this
sir.
particular relaxation will tell me, how will I know? If the value of any of these edges changes because of this relaxation, we will know that there's a negative edge cycle. So Bellman-Ford runs the Dijkstra algorithm v minus 1 times, and it runs it for the vth time to detect negative edge cycle. Okay. See, it's not necessary that if negative edge is there, it will create a negative edge cycle. It depends on the value of that negative edge, whether it's capable of creating a cycle or not. And that is only known when it's in the runtime. When it's running, when we are calculating it. Here also we are dry running it. No? We did a dry run of this graph, and we were able to see that yes, it's going to create a cycle. So it's only known in the runtime, and in the runtime, this Vth comparison will tell me that answer. What is the Vth comparison? If there's n number of nodes, the nth relaxation will tell me if there's a negative edge cycle or not. Okay.
Okay sir.
Uh, uh, um,
Sir, these two algorithm are greedy method.
Yes,
Okay.
they come under greedy methods. Okay. Um, See, to draw the Dijkstra's algorithm, you can just create a simple table. Write your source vertex on this side. Create this. Write this thing. Write all the vertices here. A, B, C, D. Initially, you have A on this side. So you have initially your starting vertex is A. So from A to A, take 0 amount. From A to B, it takes 3, right? From A to B, it takes 3. From A to C, I don't know. It's infinite. You can only find this value. See, to go to C, I have to go through ya to B or I have to go through D. So since I don't have them on this side, on this portion, I cannot say, I cannot take that answer. And from going from A to D, it's 2. Then we select the minimum values of them, except obviously what is already on this side. Okay. So A is already on that side, so we are not going to take this one. What is the minimum? 2 is the minimum. So we take that and we cross out this one as well. So we have A and then we have D. So let's see. From A to A, it's still going to be 0. From A to B, now we have two paths. I can either follow this line or I can follow this line. So I can see that obviously 3 is still less than 7. So it's going to be 3. Now check the C part. If I check here, this is 2 plus 1, that is 3. So for going from this to this, it's going to be 3. And finally, D is going to stay as it is. Next, we are going to choose the minimum. Now B and C both are the same. So you can choose any one of them. I'm going to choose B. So let's we have A, D, and then B. So we have something like what? 0, 3, and C. C is still going to be 3. It's either this one or we have to follow this one, or we can follow this path. But both are very big numbers. So it's going to be just 3. Nothing's going to change. And finally, D is going to stay same. Then we will take C. Here we took B. Here I'm going to take this one. This is A, D, B, C. And it's not going to change anything. So it's going to stay the same. And afterward, we are done. Now from this table, we can find out the path. What are the path? Let's see. Suppose I want to find the shortest path from A to C. How would I know? Look, I can tell you that to go from A to C, it's going to be 3. Some 3. Let's assume it's 30 rupees. So to travel from A to C, it's going to be costing you 30 rupees. But I want to know which path should I follow, right? I have this path. I have this path. I have this path. I have this path. Which path should I follow? We don't know that path, na? That path can be derived from this matrix alone. Let's see. First of all, take C. We have to go to C, na? Now check for where it changed, at which value changed it. Okay. See, here it's 3, no change. Here it's also 3. Compare from the last. Are these two different? No. Are these two different? No. Are these two different? Yes. So the value of C changed at this location. From where? Who created this 3? Well, look at this one. This value. Whatever is at the front is the one responsible for it. Who is at the front? D. So we know that to go to C, we need to go to D first. All right. Now I need to find the distance from D. check here. Where did the value change? Value changed? No. Value changed? No. Here, obviously, initially what was the case? 0, infinite, infinite, infinite. So this is obviously the change, right? See, here it's the latest change. Previously, it's just infinite. Here it changed, right? So we can see that where did it change? From infinite to 2 because of A. So the next element is going to be A. And we have found the path. If we take a bigger example, I think we will be able to solve it much more efficiently. Let's take this example alone.
Sir, we have to
Yeah.
write it by matrix kind of thing, or just we have to do on the graph itself and then we prepare this matrix.
If you, whatever is easier for you. I
Oh,
prefer
great,
the
sir.
matrix method, so I do this. You can also do the. You can also draw these graphs, but that's if it's a big graph, then you have to draw it multiple times. So I prefer the matrix method.
Okay, sir. Right.
Okay. Right. Okay. Okay. Let's draw the graph. Again, we are going to take. Let's take A as our starting vertex. Let me darken it a bit. Yeah. So here we have. Let's draw the matrix. Sorry.
सर आप कल भी क्लास लेंगे क्या?
Tomorrow, if Sunil sir is not present, then most likely yes.
ओके सर.
A, B, C, D, E, F, G. Okay. And our starting vertex is this one. So initially, obviously, we can just assign it infinite, 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 infinite. Then we take in A and we change the values. From AC, from A to A, obviously, this is that case. From A to B, we can see there's 6, right? So this is going to be 6. From A to C, C is still infinite, so it's going to stay that way. D is also infinite. E, still infinite. F, yeah, no. See, this is a incoming edge, not an outgoing edge. So it's going to stay infinite. Then G, yeah, G we have 4, right? So we can take that one. This is going to be 4. Now choose the minimum. Minimum is we have 6 and we have 4. So we are going to choose 4. And this is also done. So we have A and then we have G. Or you can just write the G here as well. But anyway, I like to write this fully. Okay, so A to A is still 0. A to B is still going to be 6. A to C. Can I go to C? No. To go to C, I have to go through B. There's no other edge. So again, infinite. A to D. Yes, I can go to D through via G, right? This
12 sir.
yeah, so it's going to be 12. From E, yeah, no, I cannot go there. So it's going to be infinite. F, I can go with again 12. And obviously G is going to be 4. Okay, next minimum is 6. So B is also used. So we have A, G, B. So it's going to be 0. This is going to stay 6. from C, yeah, I can see that 6 plus 2 will give me 8. And okay, now
10,
look
sir.
at this. Yeah, 6
10.
plus 2 plus 2 will give me 10. But see, Dijkstra's algorithm won't do this thing. Dijkstra algorithm, what does it say? Once an edge has been relaxed, you don't have to relax it again. Once a vertex has been relaxed, you cannot relax it again. But what we are following is the optimized version of Dijkstra's algorithm. So we are going to relax it anyhow. So it's going to be 6 plus 2, that is 10. Now E. Look for E. To go to
सर
E, we need D.
पार्डन प्लीज सर रिपीट
Yeah,
कर
yeah, yeah.
दीजिएगा क्या आपने लास्ट टाइम बोला सर.
See here, it's changing now. But
यस सर.
I already told you that Dijkstra algorithm is not going to do this. Dijkstra
यस
algorithm says that once an edge has been relaxed, you cannot relax
सर.
it again.
ओके.
Okay. So, oh right, I was talking about edges. No, it's okay. As we can see that 10 is the minimum value, so 10 is here. Okay. Basically, Dijkstra say that if there's an edge, you should not relax it again. But Bellman Ford relaxes it another time to check for what you say negative edge
मिनिमम.
cycles. Yeah. No, it's okay. It's going to be 10. Forget about what I said. Okay. It's going to be 10. Then we have E. To go to E, we need
सर
D
सर
or
वन
F.
सेकेंड सर. डाउट्स हो गया सर.
Yeah, yeah,
आई
yeah.
हैव वी कैन रिलैक्स एज अगेन एंड अगेन ना सर, when we got the minimum weight age sir.
Yeah, yeah.
Okay, thank you.
Okay. Now look at this. We have so it's D now. Now E. To go to E, I need either F or I need D. And I can see that on this side, none of them are here. So obviously this is still going to be infinite. Okay. Now F. F, yes, I can travel to F. F is still, I think, yeah, 12 is still 12. It's not going to change. And finally, G is still 4. Nothing change. Okay. Time to take the next minimum. I have 8, 10, and 12. So it's going to be 8. So it's going to be this value. So C is also used. And we have here A, G, B, C. Okay. It's going to be 0. Then we have
6 sir.
D is 6. Then we have.
C तो ये ठीक
Oh
रहेगा सर,
wait.
रिलैक्स हो चुका है.
Um, wait. There's a mistake here. A very big mistake. That is when we are traveling from. Yeah, this is going to be 8. But I cannot go to D na. This is still 12. The reason is to go to D, I was following this path, the path of C.
Yes sir.
But C is
And
not on this side.
yes sir.
Ah, okay, so it's going to be this, and then E is 12. This is going to be 12, and this is going to stay 4. And again, we will start with 8 only. Okay, so we have A, G, B, and C. Now it's going to be 0, 6, 8, and this will become 10. Updated because 6 plus 2 plus 2 is 4,
Yes sir.
10. Then E. From C to E, I cannot go, so it's going to stay infinite. From F, um, F is still going to remain the same because I don't see any other incoming edge. There's one from D. There's one from D, but D is not opened, so it's going to
C
remain.
to E we can travel, na sir? C to D and D to E.
No, we can travel, but D is not on this side, na?
D is not in
Can
our path sir.
Oh, okay. Yeah,
yeah.
got
Is
it.
Once
not in
it's
our
on the
that's it.
left hand side, we can use that path. Okay. Last is G. So G is still there's only 4. Okay. Next minimum. Okay. So next is we have 10 infinite 12. So we are going to take 10. And after taking 10, D is also used. So we have here A, G, B, C, and D. So 0, 6, C tak abhi bhi 8. Now D is at 10. Now let's check E. E is at infinity and to go there I can follow either this path. Look at here, I can follow this path, which is going to be 4 sorry 8 plus 4 is 12 plus 1 13. I can either follow 13 or I can follow 6 2 2 then 1. This is going to be 11, so obviously I'm going to take 11.
11. Yes, sir.
So this is going to become 11, and then F. Now let's see if I can decrease it anyhow. Let's see, the size of D is 10. To reach D the minimum is 10, and from D to F is going to become 12, and it's still 12. I don't see any reduction here, so it's going to stay 12, right? There's no reduction. 12, and this will remain 4. All right, next minimum, it's going to be 11, so this is also used. Here we will have A, G, B, C, D, E, and as you can see that E doesn't have any incoming outgoing edges, so it's not going to make any difference. So we can just write out as 0 6 8 10 11 12 and finally 4. And finally we have F. F will also be utilized. This is also used. Let's see if it's going to make some difference. A, G, B, C, D, E, F. See, F can only point to E. So I can just check if E can be relaxed. Other edges are going to stay the same. 0, 6, 8, 10. This is going to stay 12 and 4. Now let's check if there's going to be a significant difference. If I follow the path of D to E, then it's going to be 11. If I follow any other path, this is already 12. 12 plus 7 is going to be much higher. So yeah, C is also going to stay the same. Okay, this is sorry, E is also going to stay the same as 11. And we are done, right? We have completed our graph. All of them have been used. Now I can find all the edges. Let me try to find one, and then you guys can try to find the other ones. Okay, let's find the edge from A to, let's see, A to E. Let's find the path from A to E. Okay, I want to find sorry. Yeah, I want to find A to E. All right, first of all we will write down E. Now find where it was changed. Where was it changed? Let me take some other color. E is here. Any change? No. Change? No. Here? Yes, there is change. Who created this change? D. All right. So I know that here it's going to be D. Now I need to find where D changed. Where is D? This is D. Change? No. Change? No. Change? No. Change? Yep. Who made this change? C. So this is going to be C. Now let's find C. C. Okay. Change? Nope. Change? Nope. Change? Nahi. Change? Nahi. Here it changed. Who changed it? B. So here it's going to be B. Now we need to find for who changed B. All
G,
right.
sir.
Yeah.
G.
6, 6. Huh?
G will change, sir.
G? Who changed where? Oh, right. G changed it. Right. No. When did G change? Look. 6, 6, same. 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 Infinite to 6. Who changed it? A. Right? We are searching for who changed that value last. And if you look at here in the graph, G cannot take you to B. There's no edge. So it's logical that A is going to take you to B. Okay. And this is going to be A to B. Done. You have found your path. To go from A to E, the shortest path is this. And from this matrix, you can find out all the other edges as well. If you want to find F, follow the same procedure. Okay. Shall we do it? Will you be able to find the path for A to F?
Yeah.
Okay, find it.
It's a direct.
Yeah. So we have G there. It was changed by G. Who changed G? Change was done by A. So A to G, then A, then to F. That's it. So by this, you are able to find all the path. So you have to just develop this matrix, and after developing this matrix, you can write down these values. Write down all them: A to B, B A to C, A to D, E, F, all the path, and the weight as well. Done. Okay. So this was Dijkstra's algorithm, and it's based on the relaxation concept that I was talking about. So if you have a edge from, if you have a edge U to V, and there's some cost C, then the relax function works like this: from U to V. It checks. First of all, it will calculate the cost. The cost is calculated as the cost at U. What is the cost at arriving here? Plus the cost of traveling to C. Plus the cost of travel from U to V. Okay. This will give you the cost. And next you have to check if the cost comes out to be less than whatever is the cost of this value, whatever is the cost of V. If it's true, then you are going to update the cost of V to be the new cost. Or what you can do is, yeah, that's what's happening here anyway, is equal to the cost. Okay, this is how relaxation works. You pass in two vertices. This C is checking for the cost at this location. What is the cost at that location? These values. These values. Are they, yeah, these things. These are the cost. Infinite, zero, these things. You can find it in from the graph as well. See, I can write it like this. The cost of A to A is 0. From A to B is going to be 6. From C it's going to be 8. From D it's 10. From A to G it's going to be 4. How am I updating it? How did I update C? Or did I update D? Because I knew the cost up till here, so I just added this value, and I already knew that it's infinite, so I just updated it to 10 because that's the next minimum. Because initially Dijkstra says 0, take everything as an infinite, 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 finite, finite, infinite. Next, update these values. 0 plus 6, is less than infinite, so update it to 6. 0 plus 4 is less than infinite, update it to 4. What else? Next, take in B, the next minimum. 6 or 4 is minimum, take this one. This becomes 12. This becomes also 12. That's it. Next, take 6. Sorry, B. 6 plus 2 is 8. So this becomes this. Afterwards, 6 plus 4 will become 10. Oh, damn. Check this. We missed this one. From B to D, there's a 10 value also. 6 plus 10. Right? So there was a mistake here, guys. Anyway, it's going to be the same thing. But it's basically that you can directly travel from B to D as well. That's also a path. We missed that one. Anyway, see that was opened in this one. So it's better to double check your answers 1 or 2 times. Not a very big drastic change. Just to go to D, you just have to travel from B to D. That's it. You don't have to travel through C. It's okay. So when we had B here, this value should have changed this portion. This should have been 10. So as you can see, now the next changer is B instead of C. That's all. I think, right? You would have still chosen 8, and it would have still come out to be the same thing. It's just that it was supposed to be 10 there. Okay. Hello. Okay. I guess that was about Dijkstra's algorithm. And I think you have all submitted your enrollment number and all in the chat box. Okay.
Yep.
Yes, sir. Sir, your nice name, sir?
It's Devalai Chatterjee.
Okay. A lot of thanks, sir.
Welcome, welcome.
Yeah, sure, sir. It's a fantastic class today.
Mind blowing, sir.
Okay, thank you. If you want to reach out to me also, you can, I can share my number.
Yes, sir. Wait, sir. Yes, sir. You.
I have put it in the chat box.
Okay, sir. Okay, sir.
I am a faculty at Merit, and I usually teach these. Actually, I was going to take the class of PGDCA today, but Sunil sir suddenly called in sick, and so I came here.
No, sir. You have explained very well, sir.
Welcome.
मैंने कई सारे वीडियोस यूट्यूब पे देख रखा था सर रिकर्सन से रिलेटेड कि हम क्यों आखिरकार कांस्टेंट टाइम को हम क्यों इग्नोर करते हैं सर.
Yeah.
तो वो चीजें आपने बहुत अच्छे से ढंग से पूरा डेप्थ क्लियर किया सर. और हफमैन कोडिंग तो सर माइंड ब्लोइंग सर कि क्यों हम पहले यूज करते हैं सर. पहले आपने उसका एप्लीकेशन बताया कि क्यों जरूरत क्यों है. 8-bit रिप्रेजेंटेशन एंड सो ऑन सर. माइंड ब्लोइंग सर. बहुत बहुत दिल से शुक्रिया.
Welcome. बाकी अगर if you want to study on your own, there's a few channel like I personally prefer Abdul Bari.
Yes, sir. I have watched all videos, 163 videos, sir.
Yeah, the yeah, I when I was studying, I also studied from there only. I also had if you want to study about trees, there's Jenny's lecture. If you want
Yes, sir.
to study about recursion, linked list, and all that, again Jenny's lecture, and another one is Naresh IT technology something.
Yes, sir.
That channel is also good.
All are fantastic teachers.
Yeah. Welcome. Okay, then all the best.
Okay,
Have
thank
fun.
you so much, sir.
Okay. Good night.
Thank you, sir. Thank you.
No, sir.
Bye.
Can anybody put the YouTube link, channel link?